Okay, we'll make a start. Uh, just again I'll send an email with details. We had one class test, so there will be 3 more, 10% each. And the next one, as I said last week, is this Friday. So that is, I think, 12th of November. Is it 12th of November? Or whatever this Friday is, at the time of the tutorial. Exactly the same format in engineering building. So those of you who have got any device, bring that. Those of you who don't have to walk towards the computer cluster. And the syllabus would be trusses. So what I am realizing is some of you are asking me the questions, what is in the syllabus, and trying to find the materials. So what I am going to do is I am going to populate, there is one folder here called revision. So I am going to put the lecture notes 1, 2, 3, as well as the tutorial sheets that has been done on the topic as well as in the class in there, so that it's all in one place for you to revise. Would that be helpful? Okay. So the normal one, the learning one, is the week by week. But if you go to the revision one, you will get the main notes as well as the tutorial sheets and their answers, so in one place. So you could start revising from there. So the syllabus for the coming test is trusses from the lecture notes part 2 and all the questions related to the trusses. And many of you told me that you struggled with time a little bit last test. So I'll be extra careful with that this time. So I hope you don't have to struggle with the time this time. Again, half an hour, 30 minutes for the test. And of course, those who are assessed for extra support, they will get that, whatever recommendations it is. So that's it for the test. Anything else I wanted to say? Yes. Another piece is the group coursework that I mentioned last week. You also have to produce a group coursework for 20%. So that will be a group of 4. So please make sure that you know the groups. So there will be, or if you want to make your own group, I'm fine. So the call would go tomorrow morning. So you have got a sign-up sheets in Blackboard. So 4 of you, if you know each other and think and do well, then put yourself in a group. And then rest of you who won't be, I'll allocate you to a group on Wednesday. Okay? So by tomorrow evening, please make sure that you put yourself in a group that if you are aware of. And I'll send the instruction through email today. So you will have that, how to do that, etc. And what this particular coursework will do is, if I show you something from last year, say. So this particular coursework, which is 20%. So if I look at last year's one, so group coursework brief was something like this. So it is related to understanding and interpreting how structures work in a conceptual way is important. So the focus is that you produce a structure or you look at a structure, you identify a structure or an object, and then find out the structural principles involved with this. So marking scheme, etc. will be given. Some useful resources would be given, but best for you, I think, if I show you some of the work. This is probably where are those? Let me see the best is to go to the grade center. So it is here. What is this one? Let's see, that got a very high mark. I don't know how good it was. So they analyzed Gateshead Millennium Bridge, for example. So looks like a group of civil engineers. So they identified Millennium Bridge at Newcastle Gateshead and analyzed its load carrying capacity, so bit of the cables and also some bending moment diagram, etc. So that was one. So this group worked on a seesaw, for example, that you get into a playground. So they analyzed a seesaw here and 3 people sitting on there, and then they assumed a material, etc. Then they looked at equilibrium, shear force that will have, bending moment, etc. So it's a structural analysis they did. Let me show you a few more. So this group worked on one of the tall building, Petronas Tower, Malaysia, and then spoke about the materials as well as some amount of bending moment, axial force, shear force they worked on. So this was the final version. So this group worked on the analysis of a skateboard, for example. Okay. So presentation wasn't great, but just to show you the topic. So they analyzed. So they assumed, or they not assumed. They calculated or estimated the load that a skateboard would experience, and then did a structural analysis of a skateboard with 2 supports on 2 pair of wheels, and then the load of the person standing on them. Sorry, I should have put that on, otherwise it won't capture on the. So remind me, whatever is put on the main screen, the middle one, that's captured in the podcast. So for your future reference, if you see that what I'm saying is not there, just raise your hand and remind me. Okay. So this is the analysis of skateboard. Then the other group, next group did building again, type A 101 financial tower, and they looked at the tuned master damper. They just described it in a sense, so there was no analysis. So what we require from you is a bit of analysis. So use the structures and put the context of those in the present context to the present course that what you have learned. Equilibrium, shear force, bending moment diagram, stresses, for example. That's what you have to produce here. So although the report looks fine, but there was hardly any analysis here of this here. Some of the loads you may not know, or you won't know. You have to estimate a reasonable values of load. Next group is not great either, so it doesn't load. So move to next one. So they did an analysis of dog, for example. So the load bearing of the dog skeleton, for example, especially the backbone and the assembly. And then they put on those, so legs were 2 supports, and then they would be, and then this is the head, for example. So they analyzed the skeletal structure. Absolutely fine. And there is a fair amount of analysis going in there. So the question is, it's not just the obvious structures. So you could look at structures anywhere, even into the dog skeleton, for example. Good one, a chair, cantilever chair, for example. So they did a good analysis with this cantilever chair, with the weight getting into middle, and then what will happen to the chair in terms of the loading. Okay. So a chair is an object you can use for your analysis as well. So here again somebody did the Lamillo bridge in Seville by this famous architect over here, and then that's Calatrava. Sorry, I'm putting this. So this is one of the Calatrava bridge. In fact, do you know this bridge? Some of you, Calatrava, this Lamillo bridge in Seville, in Spain. No, Calatrava has only one bridge. He's a famous architect, bridge engineer. He has got only one bridge in UK, and that is no wonder. It's in Manchester. So if you know where the Deansgate is, so the connection between Deansgate and Salford, so there is a cable-stayed bridge there. So very small bridge. So, but that's Calatrava bridge in the UK. There are some more that is coming. One in London, big one, but that's not yet there. So I can see this. Okay, somebody did this Marina Bay Sands Hotel in Singapore, for example, and did an analysis of those structures. Now the main thing is it's not the description as such. Description is important, of course, but it is also the relevant analysis. How do you approximate the whole structure, idealize the whole structure? So the whole point is you have got this physical structure, and then what you have to do is you have to make that structures to a set of structure that you can analyze and idealize or abstract it to a beam or a column or set of a beam, column or frame, for example. Now this is not the only format I would allow. I would allow also if you want to make a small video, for example. So instead of a paper submission, and this was really a bit clever in a way because there is a page limit. So one A3 page or two A4 sheets that you could do. So what these guys do is, although I'm not saying you should do because this takes a lot of time, so they did this analysis with a video, with voice over and everything. Now, that was a little bit over the top. I don't expect people to do that. But the thing is, although they did this video, but the marks is not that high, as you could see. So it's all what you are doing that makes sense rather than. So I didn't want a PowerPoint presentation with voiceover, let's put it that way. But you could use the video, for example, instead of PowerPoint. So instead of the normal poster. So somebody analyzed a car suspension, for example. Somebody analyzed a barbell with a bit of an analysis there. So what you could see so far that I have shown you is hardly something is repeating. Sometimes some famous structural monuments are picked up and then they are repeated, but mostly it's unique. So this is a yellow crane tower. Is it Wuhan? Looks like Wuhan. Okay, so this is the yellow crane tower in China. So they have analyzed that. Okay. So okay, so you got some sense what to expect. Yeah, go on.
Because of how many 65s there were, I want to ask what makes up the marks and how can someone get a
Yeah, okay. So that I'll give you some instruction for that. So you'll get a, this is the old one, so you'll get a better briefing than that. So let me go to the last year's one, because the last year one should be much more relevant. So this is 2019-20. So this would be your mark scheme. So what to put it in there? So 70% or more, so significant insight into structural behavior and design, either extending beyond the topics covered in lecture or if limited to this topic, applying them in novel ways. Sources of information are extensive, well documented, presentation is a professional standard, communication is very clear and shows imagination using the limited space available. Now in terms of the detailed marking, I think I used a rubric. I could show you the rubric. And I'll show you some of the past submission as well, so that I'll put that in the in Blackboard as well. So some of those from the previous years I'll put that in. And in terms of submission, so there is a rubric that I don't know. There is a marking rubrics that I use, and the rubrics normally, I'll have a look at that again this year. So abstract and conceptualization is up to 15%. So what does it mean? That you have got a dog skeleton, for example, you are abstracting them to a frame or a beam. That's the abstract and conceptualization means. Or a real structure, how do you make it as a structural problem? So that's 15%. And then how good your topic is from the creativity point aspects is another 15%. So abstraction and conceptualization is 15% and creativity is 15%. So the first two would give you almost 30% of the marks. So how creative is your topic, for example? So the dog one definitely score high on the creative aspects. Or for example, the chair one, the creative aspect, it will be high compared to a standard bridge or a building, for example. Okay. Then calculation is the bulk here, which is 50%, and then the presentation is the rest 20%. So that's a simple marking scheme. So the conceptualization 15, creativity 15, calculation 50, and presentation 20. Is that okay? So I'll show you, I'll put a folder there which will, although having said that, this Golden Gate Bridge here was a fine example in terms of the calculations and everything, but I'll let you show how much in the, what was their mark. See, the creativity point, they didn't score high because that is a very standard structure in that way. Although they are very good in the abstraction and conceptualization and calculation and possibly the presentation as well, but not so high in the creativity aspect. Okay? That doesn't mean that you have to go out of the way to find something extremely creative one, but which you will fail in analysis. Analysis is 50% there. So although this is a standard bridge they have used, but the analysis was quite good, and then they got quite high marks for that. Okay, so is that fine for you to have a good review of this group coursework? So the call would go out. So if you want to select your own group up to 4 people, then please do so by signing up to the sign up sheets. And then if whoever is left out, then I'll put them in a group randomly. If as this is the group work, then there would be a peer review as well if the members do not agree that they contributed equally. So you don't have to do the peer review if each member think they contributed equally. But if you say, okay, you didn't, you think you have done more, or somebody didn't do at all contribute, then fill in a peer review or peer assessment form. So then I'll take into account the marks for the groups as well. Okay, so that's about the big piece of coursework, which is 20%, and that's what I'll be looking later. So I'll talk about that again when time comes. So what I'm going to do is, for the rest of the lectures today, is going through the sketching bending moment shear force diagram that I started last week. And there was a bit of a mistake in one of the shear force calculation. So first of all, I'll try to revisit that and then move on to the other one. So this was the first problem. So we had a point load onto a cantilever beam in this way. So we did the free body diagram, vertically upward reaction force to balance the downward load and a moment that would act. Now the mistake that we did in the, and this is the sign convention we'll choose. Now if we consider this problem as, let's say, we move from left to right, then of course there is this vertical force, and that is opposite directions to the load that is acting. So that's a negative, so that's okay. We can consider that as a negative, and no load in between. So the dv dx is w. Using that formula, we could complete this one. Bending moment, similarly, dm dx is the v. So here is negative, so it comes with a negative slope. So negative slope is important here. So if this is horizontal line, anything is good in this direction is positive slope, and it is negative slope in this direction. But that is only true if your x is along that direction. You are going from left to right. Mistakes that we made last week was we moved from right to left because there was a zero shear force, zero bending moment. It is tempting to move from right to left. But then the problem would be different, because if you're going from left to right, x is this direction. What is a positive slope means? Positive slope means for positive x, you get positive y. So if for positive x, you get positive value, so that way is your positive slope. And for positive x value, if you increase x, if y value decreases, then that's negative slope. So the same principle should be applied here. I think one of your friend Elliot mentioned that towards the end. So if you are coming from right to left, then for positive x, positive value of y would be this slope. So it is going into that direction. So which is same as this type of slope in this case. So if you are coming from the right hand side, positive slope would be similar direction as the negative slope if you are coming from the left hand side. And similarly, a negative slope if you are coming from the right hand side would be the same slope as the positive side from if you come from this way. So to take into account that, if you are coming from the right side to the left side, you use these quantities as negative, then that should be all right. So to summarize, the mistake that we made was we didn't take into account properly the moving from right to left. So for all calculations like this, you make sure that you are careful about you are going from left to right or right to left, because that will determine whether your calculations is right or not. So I'll quickly go through rest of the problems that we did. last Thursday. So the second problem was this one, was a cantilever beam with UDL. So how do we solve this problem? Okay, what we are going to do is, we are going from, say, left to right. Now, as we are going from left to right, shear force diagram, nothing, no forces. As soon as I go there, I can see that some of the forces are coming down. Now, of course, according to the sign convention, the load downward is positive, and dV dx is W. So this is the, so I'm coming from left to right, dV dx is W. So the slope of the shear force is the load. Now the load is downward, the positive, so that means shear force slope is positive. So this is the positive slope line, of course, so it will start, so it's a constant load, so that means constant slope. Now when it comes to the bending moment diagram, the formula, the relationship is dm dx is v. Slope of bending moment diagram is shear force. So slope of bending moment diagram then would be different at different point. Here the slope would be relevant to this much of shear force. Now the shear force is increasing, so the slope would increase, and also it's a positive slope. So your slope at this point is 0 because shear force is 0. Slope at that point is this much. Slope at this point is slightly higher, so much higher. Slope at that point is the highest, so that's the slope of this point. So that's how we draw, sketch this bending moment and shear force diagram using this relationship. Then there was this problem here that we did. Again, if we first of all drew the bending moment, the free body diagram, and then we looked at the shear force diagram using this relationship, dV dx is W. So if I come to this point, for example, I have got an upward force. Now horizontal force is ignored because that's a beam. So I have got an upward force. What does upward force means? It's the negative directions of W. Downward force is positive. So upward reaction force is negative. So dV dx, so here the shear force will start with a negative value. And then there is no load until here, that means slope is 0. So W is the load, load is not there at all. So the slope is 0 means it's a flat line. We come into here, and then I have got a downward force, that means a positive slope. So from here I will go into a positive slope, and then these points are point of concentrated load. You will have a sudden jump, so 90 degree slope, to be honest. So put that in, and then you will reach probably, so if you consider R2 would be less than that value, then probably you will get, so you will put qualitatively this bit higher than that one, for example, or this total would be higher than this one, and because R3 is greater than R2. And then as you go, there is no load, then again the slope starts to become flat, and until it comes there, then the R3 is upward, that means W is, so it should come down to the 0 point here. What about the bending moment diagram? Now bending moment diagram is 0 at this point, of course we know, because that's a hinge, and then it has got a dm dx is V. So that means slope of the bending moment diagram would be the shear force. Now shear force is negative at that point, and it continues as a constant value until this point. So you have got a constant slope, and this slope is R2, which is the value of the shear force. At this point, shear force changes to positive. So my bending moment would have a positive slope. And that, what is the value of the slope? That is R3. So we did that, but I thought that there was a bit of a mistake into the first problem. I would revise that. And similarly, the fourth problem, that's what we did, was this one. So again, first complete the equilibrium, and then just start the shear force diagram where dV dx is W. That means slope of the shear force is the load intensity. So at the left hand end, you have got R2s to start with. That's going up. So load convention, that means it's a downward force is positive. So upward force must be negative. So I put that as negative R2 value. Then I start to have the load which is coming down. So that means a positive load. So my shear force diagram should start to have a positive value. And it's a constant intensity of the load. So the slope would be intensity of this load, which is W. So it will probably cross this line here somewhere and starts to get a positive value of shear force at this point. And from there, there is no load, so you will end up into this position. And when you go to the right hand support, upward force, that means it will come down to this point with a negative slope. So from there, if you continue, zero slope, and when you come to this point, it's a negative slope, so you are turned back into zero value. What about bending moment diagram? Slope of bending moment diagram is the shear force. So you start with a negative slope, and you could see the slope is becoming less and less negative. Ultimate, or the value of the shear force is becoming less and less negative and zero at this point. So that would be the slope as well. So it will start with a high negative value and it will start to decrease. Ultimately at this point, slope is zero because the shear force is zero at this point. And then it will be starting to getting positive with a curved one until this point, and then from this point it would be a flat line because the value is constant. So these four, we did it last week. All of these were okay except the first one, F. That's where we made a mistake of not taking into the sign, which is if you are coming from the right hand side, actually positive slope is this one, which is the negative of that. So that was the mistake. Okay. Is that okay so far? This one I emailed you the answer or solution up to this point. Yeah? Okay. So the fifth problem is this one. Fifth problem is little bit difficult because so fifth problem is here. So you have got two loads, one as an UDL and one point load. Now the reaction force from the pin would be R1 and R2 and roller would be R3. But we don't know which direction would be. Why? Because if you consider two sets of loads separately, if you don't consider the point load to start with, let's say you have got the UDL, then the reaction force would, of course, this UDL would be supported by these two. So both would be upward. Okay, because the load is in between these, and the beam would deflect in this way, right? Beam would deflect that way over this span. But what happens is when you consider that point load, what does it do? So the point load is here on the right hand side, and you have got two supports. So what is the effect of point load with respect to the right hand support would be? Now you can if you consider your pivot or lever here, and you have got this beam, and then you are putting a load onto this side, then the other side will try to lift off. So this support will try to lift off, for example. So R2 would be, and the point of this support, the pin support would be try to pull it down to the ground. So due to this load, point load, there would be a downward reaction force. So imagine, again, you have got this beam and you are putting a load, and then the point of rotation, let's say this support, and you put a load in here. Where does this end will go? It will go up like that. So if it goes up like this, of course this point is connected to the ground by this pin. It cannot just move up. So what does the pin do? Pin will try to pull it down towards the ground level. So you'll have a reaction force which will be coming downward. Yeah.
But there is a load aspect that will give a...
Yeah, so the two loads I'm considering separately, the effect on the reaction force. This one is fine. This UDL would both try to push the beam towards the ground. So the reaction force from the ground would be upward. So due to this load, both reaction force would be upward. That's fine. But due to that point load, the reaction force onto the other one would be vertically downward rather than the upward reaction force. That's the point. Now, whether if we add them up together, whether the net reaction force at the left hand support would be upward or downward will depend on how big this load is compared to that load. So if this load is very big or the effect of this load is very big, then there will be a net downward reaction force. Or if the effect of the point load is less compared to the UDL, then there would be a net upward reaction force. So this is one thing that for this qualitative diagram you need to consider. But first of all, let's say that we have got a both net upward reaction force. So the normal way. So the F is relatively low. So how does the shear force diagram would look like? dV dx is W. So I have got a upward reaction force, that means it's a negative shear force. And then I have got a downward load intensity, so that means a positive slope. So I start with a negative value of shear force because R2 is upward. So I am here, but then I have started to experience a positive load, which is downward load. That means positive slope. So maybe I'll go across this line here and I'll go there. And there is no load between this, so slope is 0, so we continue there. Then R3 comes in. So I'm moving from left to right. Then after this, R3 comes in. Now R3 is upward. So the load upward means it's a negative. So my slope at this point would be rotating to a negative 90 degrees. So I'll come down to this point, for example. And then there is no load, so that means 0 slope, and ultimately I'll come here. Again, load downward, that means a positive shear force. So I'll bring back to this point. So again, just looking at the the load intensity, I can complete the shear force diagram. If you move from right to left, you have to use this sort of diagram, and you can simplify that dV as instead minus W and minus V, and be careful with the positive slope and the negative slope in that case. So then you will get to the same conclusions. What about the bending moment diagram? Now the bending moment diagram is, we know dm dx is equal to V. So in terms of bending moment diagram, we start with a 0 moment at the hinge, and then we have got this much of shear force. dm dx is V. So I'll start with a negative slope, and it's a negative bending moment. And what I see is the shear force, it is becoming less and less negative until 0 at this point. So my slope would start to become less and less negative until this point where shear force is 0, my bending moment slope would be also 0. And then it starts to increase in positive value. So my slope would start to increase until this point. And then it has got a constant slope, I go that way. So I am at this point, and then from this point, the shear force changes positive to negative, so my slope will change abruptly from positive to the negative slope. Okay? And then, of course, there is no load, nothing, and a free end, so there would be no shear force, no bending moment. Now, this is assuming the effect of this load was lower onto the left-hand support compared to the effect of the UDL. But what if it is otherwise? If F is a high force, then we would expect R2 to come downwards in this case. And if R2 is downward, then shear force diagram would be little different. So R2 is downward, means it is a positive load in that sense. So it starts with a positive shear force. And then load is coming down, so that's a positive slope as well. So it will go up to this point. And then no load, zero slope. And then upward load means downward shear force. And then again, so this bit is fine, but only that bit is start with a positive shear force. So bending moment diagram would accordingly change. So you start with a positive slope in here. So you start with a positive slope and the slope would start to increase up to this point. And here to here is a constant slope, and then this bit is the same. So this is when you could have qualitatively, you don't know the value of the force. But if the numbers are given, then it's easy. Then you can easily find out whether R2 would be upwards or downwards. And then you can do the calculations.
For the first case, why does the slope crossover, the line crossover?
Why the line crossover? Good point. So if you consider R2 and R3 in this direction, so R2 would be effect of this load. R2 you can expect is less than the total load. So if the total load is bigger than R2, then of course it will cross this line at some point. Not exactly sure where, but it will cross that point. Okay, any other comment from this one? Again, this one I'll upload in the Blackboard anyway, so this solution. So that is another one. Part F is very similar to this one, except you have got a horizontal force. So that will not affect the shear force and bending moment diagram. It will just have another axial force in there. But G is slightly different, so I'm going to show you the part G. So G has got this force system. You have got an UDL and a triangularly varying load. So the reaction force free body diagram wise would be like this. What about the shear force diagram? So again, we go dV dx is W. So this R2 is upward. Now here also the same argument you can make, that if this load effect is higher than that load, then you need to do two sets of calculations. But for this problem, let's say, okay, this would give a upward reaction force, both places. So R2 is upward, so that's negative load direction. So I start with a negative shear force. And then the load is downward, so that means the intensity is positive and the load intensity is constant. So I go with a positive slope up to this point. Then there is no load, so slope of the shear force diagram is 0. Once I come through this point, then I've got R3, which is opposite to the sign convention for the load. So that means it's a negative slope. And because R3 is concentrated, of course, it's the load intensity over a small in distance is very high. So almost 90 degree slope. And then you have got a load coming down, but this load decreases with intensity. So very high intensity at the start, and it's a positive load. So I'll start with a very high slope, a positive slope, and then load intensity decreases and becomes 0 at this point. So my shear force diagram would have a slope which will be positive and start to decrease, and ultimately it will be 0 at this point. So the load intensity decreases for a triangular load in this case, so the slope would also start to decrease. And it will be 0 at this point, load intensity, so the slope would be 0 at that point as well. And I said this is a second order because it is increasing linearly, and so the shear force would decrease in second order, one higher order. And I could use the same thing to calculate to draw the bending moment diagram. So my shear force is negative to start with, so I start with a negative slope. And I go on until this point. So what is this point? This point is here. Until that point, my shear force is becoming less and less negative and to 0. So that's what I'll do. I start with a high slope. My slope would start to decrease and until this point over here, when the slope would be 0 because shear force intensity is 0 at that point. So the slope is 0. Then it will start to have a positive value. So it will start to increase. And then from there to there is a constant slope. And from here there is a change in slope from positive to negative. So at this point, you had from the left hand side is a positive slope, but suddenly your shear force is negative. So the slope of the bending moment diagram would start with a negative value, and then it will start to become 0 towards the end. So that's what, so it is another 1 degree higher than that. So that's the third degree. And again, as I say, you could consider another case where R2 is downward if the triangular load effect is more. Yeah.
How do you know the difference in terms of plotting for second and third order curves? It is not second and third.
Yeah. So if the intensity is constant, then that's a line, right? So if you draw that intensity, that's a flat line. So here the intensity is decreasing. That means slope would decrease. So that's sort of a parabolic curve or a second order curve. So if from a straight line to a second order curve, you'll see the graph would increase. Now, if it increases linearly, that means slope would increase linearly. If it decreases linearly, slope would decrease linearly. So that will give one higher order of the curve. Yeah. Yeah. So you can use that with a calculus, for example. If you have got an expression, say y equal to ax square plus bx plus c, a second order curve. So what is dy dx? Dy dx is 2ax plus b. So that's a linear line.
Yes.
So conversely, if a slope is linear line, the curve must be a second order.
And the shear force thing is equal to the...
Yeah. Third order in that case. Yeah.
Okay. The shear force, so this diagram above is the gradient of the shear force diagram,
Yeah.
which is the gradient of the bending moment diagram.
Exactly.
That works.
So not gradient of the shear force diagram, value of the shear force diagram is the gradient of the moment diagram. Yeah. Okay, so time is up. So what I'm going to do is quickly, there are a couple of other problems that I'll probably upload the solution for this. So you'll get the solution for this one. For the next tutorial sets, please start to go through the next tutorial sets, and I'll upload first couple of problem solution, and the rest we'll do it on Thursday. Okay? So please make sure that you complete these 2 tutorial sets by Thursday. Thank you. Hi Ben, you are okay? Not bad. So you are doing instead of Alistair this one, is it? Yeah. Just 1 second, give me a second, let me switch off so that the Ben Rogers can do it. Just give me a couple of moments. Okay, let me put on my mask. Okay, go on, tell me.
Sort of coursework question, but I was sort of here 2 weeks because I had to go to Sri Lanka for my grandparents.
Okay, yeah.
So
It's all through mitigating circumstances.
I completed the mitigating circumstances, but they didn't get to me yet.
That's nothing I can do. Probably they are looking at it. It depends on the committee's meeting, because they don't. So you submit the mitigating circumstances form, and there is a committee within the department will look at your mitigating circumstances, and they have got a set frequency. So maybe every 3 weeks or every 4 weeks, and then your submission will go to them, and then they will put the recommendation, and then you will hear from them. So that's the process. Yeah.
I just want to ask you about like this is a breathing moment. Why does it like become linear?
Because then the shear force must be slope is zero.
So the slope is zero, it's linear.
The slope of this is the intensity of that. So if that doesn't change, the slope remains constant.
Quick question. Where do you know exactly where the
No, that's
crosses the...
that's somewhere there.
Oh, okay, thank you. So the process...
You know that method you use, so you put a piece of paper, so it's like a lesson, you put a piece of paper there and work out the force. So you know when you get to the very end, where would that piece of paper go?
It probably you have to just then flip it over towards the end to go on to the right hand.
Start right.
Then you can think about it the right hand side also. Because if this is the edge, you are moving to the edge, then you'll fall off. So what's happening in the edge, you have to come from the right. See you, Ben.
Here.